This is the last set of lectures on sort of really thinking about things, computational difficulties we're going to face when we move to solving real problems. It is not enough to just get the solution. Your job is to get the solution most accurately and as fast as possible. If you use the generic ways of solving things, oftentimes you get yourself in a position where you're going to solve Ax equal to B, paying order n cubed. And if you're doing that professionally, you're going to get fired. You need to actually solve it in a smart way and solve it in a way that's computationally tractable. So as we start thinking about these things, we also have to think about difficulties that it can arise in a variety of these complex PD systems that we want to address. Even not very complex PD systems, there's always issues we have to face and start thinking about handling ahead of time so that they don't sneak up on us and have problems. In fact, one of the things that we want to do is already start doing the saying of the observations of troubles that are down the road for us, even in terms of shallow water wave equations. So again, I love the shallow water wave equations because they already start, even though it sort of doesn't seem that difficult, they produce very nice dynamics. There's already problems immediately that arise and start when you start a little bit deeper dive into what am I actually doing with the solution technique. So remember, this is just the Poisson equation, but with periodic boundary conditions. And if you don't think about it, you think there's no problem with this. It's just discretize, solve. There's a huge problem with this, and let me show it to you. When you discretize this into Ax equals to B, I'm going to ask you first the following question. If I had a solution to this, let's call it phi 0, and if I had a constant to it, so here it goes, here's a new solution, phi 0 plus a constant, is that still a solution to it? And in fact, if you plug this in, remember, if I plug this in, this is 2 derivatives in x, 2 derivatives in y, which means it erases that constant c. So the constant c has no impact on the solution here, and that constant c actually has no impact on the periodic boundary conditions either, because that constant c is on both sides. In other words, what I'm telling you is there's an infinite number of solutions. Okay? So what does that mean? What does the consequence of that mean? Remember, we took this del squared psi, we basically discretized it into this large Ax equal to B system. What does it mean to have an infinite number of solutions? Well, that means that the determinant of that matrix A was 0. And the one thing you always had to watch for, the only thing you had to be careful of in linear algebra when you're solving Ax equal to B is to make sure the determinant is not 0. And the determinant is 0. Because you have an infinite number of solutions. In fact, the determinant of the solution being 0 either meant you had no solution or an infinite number. And in this case, it's really easy to show there's an infinite number. And by the way, same thing happens if you have no flux boundary conditions in this as well. So there's two scenarios here where I have an infinite number of solutions, and you've got a problem now of how you're going to solve this, because when you solve this, you're trying to tell it, solve Ax equal to B computationally for something whose determinant is 0. This is a terrible idea, and if you're not paying attention, you'll try to do this anyway, not realizing you're in this scenario. Okay, so we want to figure out a fix to this. Well, here's a simple fix. If the determinant is 0, right, and that's what we have, then what we want to do is figure out how can I make the determinant not 0. So one easy way to do it, in other words, there's an arbitrary constant there. You saw this, right? I can add a constant to the solution, still a solution. So essentially, there's this arbitrary constant I have to pin down. So one way to do it is just simply say when I discretized, on the diagonal, let's say the first diagonal is supposed to be -4, I'll just change it to 0 or 3 or 10, anything other than -4. And what I did by changing one equation of my system of equations is I took this matrix A, which was determinant was 0, and I made it now determinant's not 0. So now it's much better conditioned, and now I can solve the Ax equal to B problem simply by this simple change. And notice, this is in the corner of my domain. So it has essentially what this is doing is pinning down a specific constant C. That's it. So again, you can do other kind of things that you want, but this is a very simple and quick and easy fix if you want it. Okay? These are the kind of pro-level tips you need when you solve things, and also that you have to be aware of. The easiest way to check to see if this was a problem is to take the matrix A you built and compute the condition number by doing cond A. And if it's big, like 10 to the 15 or 16, you know you're in the situation where the determinant is basically 0. And so you need a way to fix that. Here's a simple way to fix it. Okay, so that's a really practical trick, because now what you did is said instead of any constant c, it pins it down to one of them. Do I care which one? Because you might make you uncomfortable, but notice, when I solve for the stream function or vorticity, psi is never alone. I'm always, in those equations, it's always psi of x or psi of y. So the additional constant is always out of there. Notice that when you take a derivative, the constant disappears. So doing this doesn't affect my solution at all. At all. Okay? Partly because the only thing that shows up in those equations is psi when it has derivatives. Okay, do you get around this if you do an FFT? Right? So that's a matrix that has a determinant 0. I still have the same issue if I do a fast Poisson solver like this with an FFT. In fact, if you go back to the FFT lecture on this, the way we did this is we took Fourier transform in x, Fourier transform in y, and that gives you a minus kx squared minus ky squared, and I can divide that through to get this representation here. So here is the solution of the stream function in the Fourier domain, and all I have to do is invert this. So what's the problem? The problem is, what happens when your kx and ky are 0? Then you got to divide by 0 problem. So the equivalent of a determinant 0 problem in ax equal to b is a divide by 0 problem in the fast Fourier transform. And that's exactly what you have here too. And we need a fix. Otherwise, as you run your code, you're having to divide by 0. You're trying to make your code divide by 0, right? Which is a terrible idea. Okay? So how do you fix it? Same thing, you know, it's as easy as a fix as we did in the Laplace equation with the matrix A. We just took one cell, the -4, changed it into something else. Same thing we can do here. Instead of the 0 wave number, k0, kx0, or ky0, in other words, the one that's creating the divide by 0 problem, instead of being 0, which it is when you build it, you make it -10 to -6, something like this. Something small. So essentially, you just added a perturbation, but all of a sudden this becomes not a divide by 0 problem anymore, and it's a perturbatively close. Why 10 to -6? You know, this is only going to be 10 to -12 when it shows up here. Your time stepping algorithm is usually 10 to -6, so this is going to make no impact practically on the solution. And what this does is, again, just like before, it determines the constant c in the stream function, making this well post. Okay, so in other words, that problem of an infinite number of solutions had to be handled if you're using the discretization of ax equal to b or in the Fourier domain, and we found ways to handle it in both ways. And their manifestation of a problem is a divide by 0 here, and in the other case it's the determinant being 0. Super practical things to think about, and you always want to understand your problem before you start solving it so that you don't think you have something that's correct when it's just wrong. Okay? Final things we want to do is talk about derivative matrices. So far, we've talked about the A matrix before, which was 2 derivatives in x and 2 derivatives in y. But we really want to do, you know, what showed up in our stream function equations and vorticity and stream function pairings is derivatives in x and derivatives in y. And so here's the derivative in x here, right? So if we take the derivative of the vorticity in x, this is just our essentially one derivative formula. This is a simple second order difference formula. But what we have to do is organize this also, again, like we did before. Let's write in our notation, go to the mnth position. This is the way it looks like. And then this becomes a system of equations. And as we organize our vorticity, all of this just becomes, if we arrange the vorticity this way, it's just a matrix multiply. So there's a B matrix that we've constructed here, and the B matrix, hitting this matrix here, takes a derivative in x. And if I wanted to do that too with the y direction, in other words, how do I do a derivative in y, let's call that a C matrix. So B takes this vector here, produces a first derivative in x, and the C matrix we can construct would produce a y derivative of just with a matrix multiply as well. So what this allows you to do is once you've constructed this, and by the way, here's what the B matrix actually looks like. It's n squared by n squared matrix, and so you have to, figure out how to construct this. That's part of your homework to do, is to figure out how did this actually result, given that my data was stacked like this. It's not that hard to work out. It's a lot like building that A matrix. You have to go through that process once at least to make sure you understand the A matrix, which is two derivatives in x and y, understand the B matrix, which is derivative in x, and then there's a C matrix, which was one derivative in y, which looks different than this one as well. But once you have those matrices built, then computing something like this Poisson bracket between these derivatives, just as matrix multiplies all the way across. It's as simple as that. If you mess up anything in the ABC matrix, your solutions are just wrong. So getting accurate ABC matrices is coming back to, again, the organizational part you're responsible for. That is your responsibility. That is entirely your code setup, is how do I construct ABC to do the derivatives? Because once I have them, everything else is set up now to go to time stepping. And that's what we want to really engage in next, is how do I do time stepping? Because now I have all the matrices set up to go about the process of solving that into the future. So these are just practical tips and how we handle things. But all of these things have to be handled carefully and thoughtfully, and you have to be aware of them. You can't just blindly solve these equations. These equations often will have things. Again, when we solve that stream function with periodic boundaries, you have to understand that if there's an infinite number of solutions, your numerical code is going to break unless you take care of it. So you can't just simply check your brain at the door. You've got to engage fully in the problem and understand what are the things that you have to take care of before you just start computing away. Because once you start computing and get the algorithm right, it's really very fast from there, but you have to get everything right. So these are just lessons in how to overcome the computational difficulties that you're going to face in all kinds of problems all the time. And so it's your job to really kind of understand how to address them and the possibilities of addressing them as you go forward.